In this video, we're starting off with a polar curve, and we want to find a representation of it in Cartesian coordinates. Or in other words, we're going to take this polar curve and find the Cartesian equation that represents the same thing. All right, so the polar curve we're given is r is equal to 6 times the sine of theta. So our goal here is basically to use our transformation equations between polar coordinates and Cartesian coordinates, get rid of all the r's and thetas to have an equation fully in terms of x and y. So I want to begin just by making two observations. The first observation is that I can always take x squared plus y squared and get r squared back. Or in other words, from our Cartesian to polar set of things, we have r squareds equal to x squared plus y squared. So if we take the square root of both sides, we get r is equal to plus or minus the square root of x squared plus y squared. In other words, anytime we have just an r by itself, like we do in the original, we could just substitute in a plus minus square root of x squared plus y squared. So whenever we have just an r by itself for that matter, we can always do that substitution. The second thing I want us to observe is, well, what happens if we just have sines and cosines? So we can always take sine of theta or cosine of theta and rewrite it in terms of x, y, and r. So for example, let's first take the x equation. X is r cosine of theta. If we divide both sides by r, we just get x over r is equal to the cosine of theta. So anytime we'd have a cosine in the equation, we could substitute a x over r. However, in this case, we don't have a cosine. What we do have is a sine. So if we can do the same process for the other equation though, y is equal to r sine of theta. If we solve for sine, we get y over r is equal to sine of theta. So in our original equation, we can take that y over r and substitute it in for where we have sine of theta. So let's go ahead and actually make that move first. So we have r is equal to 6 times sine of theta, which we just saw is equal to y over r. Next, we can multiply both sides by r. Again, the reason for doing that is on this right-hand side, you can see that the r's will cancel. The left-hand side, we'll get an r squared is equal to 6 times y. This last step, basically what we did was cross-multiply that denominator of r over to the left side. But now that we have r squareds equal to 6 times y, we can use that first observation that says r squared is equal to x squared plus y squared. So if we substitute that in, we get x squared plus y squared is equal to 6 times y. And well, at this stage, we've taken a curve in polar coordinates that has r's and thetas, and we've successfully converted it to an equation in Cartesian form because there's only x's and y terms. So likely we could be done at this point if we'd like. However, I'm going to take this a step further just for some extra practice. We're going to be able to show, spoiler, that this thing's actually a circle. Now, in order to do that, we'll get to practice some algebra. So full disclosure, at this point in the problem, what we found so far is an equation fully in terms of x and y. So we've taken that polar curve that we started with and successfully converted it into Cartesian form. We're just going above and beyond in this next little bit. So if we subtract that 6y from both sides, we'll have x squared plus y squared minus 6y is equal to 0. Now, maybe I should tell you where we're going here. If you remember the general form of a circle, we could think of as the following. We could have x plus or minus some number, say a, quantity squared, plus y plus or minus some number, say b squared, and that would be equal to the radius of the circle squared. So we can think about that in terms of our circle. What are we looking for here? Well, in this problem, we don't have any a terms since we just have an x squared. So in this particular problem, we can think about as a is 0. However, this b term, if it's plus or minus b, in this case, this is not going to be equal to 0 because we have already y squared minus some other term in terms of y. So this is going to be actually something that we find now. What is this b that we need? And in order to do this, we're going to get to use a little mathematical tool called completing the square. So I just want to start by grouping the y terms that we have. We have y squared minus 6y. And now we're good to start completing that square. Now, the first thing to remember for these types of mathematical operations, when completing the square, the whole end goal is we're adding 0 to the problem. Of course, 0 doesn't look like 0. It looks like plus some number minus the same number. So again, what we're going to do is subtract some number and then add that same number inside those parentheses. Adding the same number and subtracting it, we get an overall sum of 0 for that. So we're not changing this anyway. All right, but the question is then, well, what is this number that we should use? And this is where completing the square basically comes in. What we're going to do is notice a couple things. The first thing, we have a minus sign here. So what that means is in the x or the y term that we want, we'll want y minus some number. Okay, that's looking for the future. But in terms of going towards completing the square, let's focus on this 6 for a moment. What we're going to do is take that 6, divide by 2. So minus 6 over 2 plus 6 over 2. But we're not done yet. Each of those terms, we're also going to square them. All right, so let's see what we have now. We have x squared plus the quantity y squared minus 6y. We'll have minus a 3 squared plus a 3 squared. And that still equals 0 on the right-hand side. All right, so just squaring those terms, we have x squared plus y squared minus 6y. We'll have a minus 9, and we'll have a plus 9. So this is where we said we made that other observation that the sign in front of that 6y term was negative. What that means is when we square this thing, we'll actually need to group that plus 9 term with it. So if we take those terms, we'll have this y squared minus 6y plus 9. Again, those are the terms that I just grouped together or highlighted in the previous line. We still though have that minus 9 term from the previous line that we have yet to touch. So we have minus 9, and that whole thing equals 0. This minus 9, we'll be able to add to both sides of the equation. So let's just add that to both sides of the equation. So we have x squared plus, we'll still have that same term in parentheses, y squared minus 6y plus 9, except now this equals 9 on the right-hand side instead of 0. And our next goal is how can we take this and write this as a quantity squared term? Well, the factors of 9 that add up to minus 6, we have factor that into a minus 3 and minus 3. So what that means is we can write this as x squared plus the quantity y minus 3 squared. So this thing equals 9. So we've actually just found now, again, this is taking that same equation that we had before. We've done some completing the square stuff on it, and we've actually shown that the equation that we found in Cartesian form represents a circle. So at this junction, we actually have an equation that describes a circle for us. Let's take it one little step further. So we have x squared plus y minus 3 squared. And to put this in a circle form, we can take the square root of the right-hand side and square it, just so we know what the radius of that circle is. So if we take the square root of 9, we'll get that it's 3, and we'll square that term. So what this means is this circle that we're ending up with here, there's a few things we can say about it. The first thing, the radius of the circle is 3. And this point, or this circle, is centered at x equals 0, and it's centered at y is equal to 3. So this is a circle of radius 3 centered at the point x equals 0 and y equals 3.